Good day, welcome back to part 4 of our discussion on optimization and another opportunity to work through a common example. So in this video we are going to investigate the following. Determine the dimensions of a cylindrical can whose volume is 1,000 cubic centimeter and minimizes the material used in its construction. So this seems like a very realistic problem. We want to construct a can of a certain size, i.e. volume, while minimizing the associated materials. So let's go ahead and see if we can represent this with a picture and introduce a little bit of notation. So we have a cylindrical can, and one bit of information that we are given is that we want its volume to be 1,000 cubic centimeters. So let's recall the formula for volume. If we want the volume of a cylinder, that is found as being pi r squared h, where in this case the r would represent the radius of the cylinder and h would represent its height. And note this formula should make geometric sense. Pi r squared would be the area of, say, the top or the bottom circle, simply multiplied by the height. Now to think about the quantity that we would like to minimize. That would be the material used, i.e. we want to minimize the surface area of this cylinder. And I think the most intuitive way to think about this would be to break it down. This cylindrical can really has three components: the material that makes the side, the material that makes the bottom, and the material that makes the top. And you don't have to break it up in this way, but this helps me to kind of visualize what's going on. So we have the top and the bottom, and then we have the sides, which we could roll out flat. And if we can now find the areas of each of these three pieces individually and add them up, we would have the surface area formula for the cylinder. Now note, the top and the bottom circles for this cylinder have radius r. And the area of a circle of radius r is pi r squared. And there's two of them. We have one for the top, one for the bottom. Then we also have to add onto this formula something corresponding to the sides of the cylinder. When we unwrap the cylinder, it's still going to have that height h, but its length now for this resulting rectangle would be the circumference of that associated circle making up the top or the bottom. So the circumference would be 2 pi r. And we now have the desired surface area formula that we hope to minimize. And just to reiterate, we get this first portion coming from the surface area of the top and bottom, and the second portion coming from the surface area of the middle part of the cylinder, which rolls out to be a rectangle with base length 2 pi r, height h. Now, as usual, in order to minimize this, we want to get it down to a function of a single variable. But if we look above at what we started with, we can solve for h. H is 1,000 over pi r squared, and then we can immediately substitute that into our formula. So the surface area as a function of that radius r will be 2 pi r squared plus 2 pi r times 1,000 over pi r squared. So we have a few bits of simplification here. The pi's cancel, and the 1r on the top cancels off one of the r's, but not both of the r's on the bottom. And creating a little more space here to work, we have S of r, the quantity that we want to minimize, is 2 pi r squared plus 2,000 over r, and we are going to minimize this on what interval? And this is maybe something we need to think about for a moment. R is representing the radius of our cylinder, and the cylinder has volume equal 1,000. So we think, how small could the radius be? Well, it's not really technically correct, but it certainly can't be negative. So we could say 0 is what bounds it below. And in terms of what bounds it above, well, if the height is really small, the radius would have to grow really large. So it turns out there's no single value that we can bound it by above, but really any positive quantity could represent that radius. So we need to minimize on this interval from 0 to infinity. And at this point, it has become a purely calculus problem. So let's go ahead and differentiate and see if we can find the critical points. So differentiating with respect to r, we have s prime of r is 4 pi r minus 2,000 over r squared. And it's always worth reminding ourselves, when you want to differentiate something like 1 over r, you can write it as r to the minus 1 and simply differentiate it with the power rule. And before setting this equal to 0, we could go ahead and get a common denominator. We could multiply the first piece by r squared over r squared, and we would have 4 pi r cubed minus 2,000 all divided by r squared. And what we would like to do is set this equal to 0 and see if we can solve for the critical points. And this fraction is equal to 0 precisely when the numerator is 0. So 4 pi r cubed minus 2,000 is equal to 0, which implies, what, 4 pi r cubed is 2,000. So r squared would be 500 over pi. So we would have r is equal to plus or minus the square root of 500 over pi. And that gives us a single critical point to worry about. We are thinking of the interval from 0 to infinity, and what is the sign of this derivative s prime? Well, the critical point given by the square root of 500 over pi most certainly lives in that interval. And if we go ahead and look at our formula that we have for s prime, and pick your favorite one to work with. If we start off with a small input, so let's say we input the number 1, we would have 4 pi minus 2,000 over 1. That is most certainly a negative quantity. And then if we substitute in something really large, think something like 100, then you would have 4 pi times 100 cubed, so that's quite large, minus 2,000. So that will be positive over 100 squared, which is positive. And you could figure out precisely what these numbers are, but as I've mentioned previously, as long as you are correct in where it's negative and positive, you can certainly just include those signs above the number line. And this tells us exactly what we want to see happening. We start off at some value with our function s at 0, and on this interval we decrease down to our critical point, and then we increase indefinitely. So at this critical point, the first derivative test for absolute maximums and minimums guarantees that it will be an absolute maximum. But let's just recall what it is we've been asked to find. We've been asked to determine what are the dimensions of this cylindrical can that will minimize the material used. So let's put this all together. We've determined the radius that would correspond to the dimensions that would minimize the material used. We just need to know, for this radius of the square root of 500 over pi, what would the associated height be? So let's just make a small observation below. We have the height is 1,000 over pi r squared. So if r happens to be the square root of 500 over pi, note these dimensions work out quite nicely. R squared becomes 500 over pi. The pi's cancel, and 1,000 over 500 is simply 2. So our conclusion, by the first derivative test for absolute maximums and minimums, the dimensions that minimize the surface area and note, we could write this in many ways here. We could be more specific and say that minimize the material used when constructing a cylindrical can whose volume is 1,000 cubic centimeters, but I think this simpler statement gets the point across. By the first derivative test for absolute max and mins, referencing what we have used to make this conclusion, the dimensions that minimize the surface area are when the radius is the square root of 500 over pi centimeters, and the height, as we compute it to the side, is that associated 2 centimeters. And that finishes up our current example. And once again, we are at this ideal point for you to continue practicing examples, because note, these are not easy examples, and the more we practice, the quicker, the more efficient they will become. And as usual, we're at the point where if we were meeting in person, I would have a worksheet for you all to work on. But since that's not happening, we're going to do what is second best. You all are going to go to Canvas and find the associated optimization worksheet, and you're going to spend some time working on it. And in our next video, we will go over one of the problems, number 5, on that worksheet. And I highly encourage you to take the time and work through these problems, really focusing on the procedure that you use to set up and solve the problems. And furthermore, as usual, you can find full typeset solutions on Canvas for the worksheet as well. So stay tuned and take care.